So last time we talked about postulates 2 and 3. Said that postulate number 2 says that for every property of a system, there corresponds an operator, which must be Hermitian, also linear, in fact. And postulate number 3 says if any property of the system is measured, the only possible outcomes are the eigenvalues of that operator. So we said we want that operator to be Hermitian because we want eigenvalues to be real. Okay, and we have already proven that Hermitian operators have real eigenvalues. We want real eigenvalues because if we want to measure something physically tangible, then that means it has to have a real number associated with it. Okay, and so we started talking about how to construct those operators. That's actually part of postulate 2. Okay, so this is really a shortened version of postulate 2. So part of postulate 2 is how to construct the operators. And so we started talking about position operators. Basically, we said a position operator is just a multiplicative operator. So the idea is if you want to construct the operator, you write the expression using classical mechanics in terms of position and momentum. Any position that's in your expression, any coordinate that is in your expression for that property, you replace that with an operator that simply multiplies what it operates on by that coordinate. Okay, so a position operator is just a real multiplicative operator. And we did a few examples of that. And then we said that in your expression, if you have a momentum operator, okay, if your expression has a momentum expression in it, then replace it by the momentum operator. And the momentum operator along a given coordinate q would be hbar over I, partial derivative with respect to q. And you can see that this is a derivative operator right here. Okay, by itself, a derivative operator is not Hermitian. We've proven that. But there's an I here. By putting that I in that expression, that makes the entire operator Hermitian. Okay? So done that. And then we said a kinetic energy operator. Kinetic energy is just p squared over 2m. So it's really just, that means that your kinetic energy operator is really nothing more than negative h bar squared over 2m times the momentum operator applied twice. Okay, and so in the case of for motion along the x-axis for particle number 1, then the kinetic energy operator associated with that is negative h bar squared over 2 times mass of particle 1 times the second derivative with respect to the coordinates of particle 1. Okay? And we also introduced this shortcut right here, the Laplacian or del squared operator, which is the sum of all the second derivatives, okay, with respect to all the coordinates of your particles, x1, y1, and z, x, y, and z of particle I here. This is the expression, second derivative with respect to the x coordinate of particle I, plus the second derivative with respect to the y coordinate of particle I, plus the second derivative with respect to the z coordinate of particle I. So that's your del squared operator. And so you can say your kinetic energy operator for particle I will just be negative h bar squared over 2 times the mass of particle I, del sub I squared. Okay? So we have that example. And so let's move on to potential energy operators. Quantum mechanical operator that corresponds to the potential energy is a multiplicative operator. So it simply multiplies the function by the classical expression that defines the potential energy as a function of coordinates. You've heard of kinetic energy being energy due to motion, right? Potential energy, we say, is energy due to position. So in the classical expression for potential energy, you'll have a function of coordinates. So all you have to do is replace each of those coordinates by a coordinate operator, and all it does is really multiply. It just multiplies the function it's operating on. Okay? So here's an example. Let's assume that there are no forces acting on the particle in the system. If there are no forces acting on the particle in the system, then you say the potential energy is constant. Let's try to understand why that is. What does it mean when potential energy is constant? If you leave your system alone, okay, kinetic energy plus potential energy would be constant, right? If your system is all alone by itself, total energy remains constant, law of conservation of energy. So potential energy and kinetic energy are constant. The total is constant, right? So what happens if potential energy is constant? Then the kinetic energy is also constant, right? And if the kinetic energy is constant, that means it's moving at constant speed, constant velocity. It's not accelerating. So that means what? Acceleration is 0, right? What's the force on the object? The net force is 0. So that's what we mean if there is no forces acting on the particles, you say that the potential energy is constant. Now, as a matter of convenience, we can take this constant as 0. There's really no absolute scale for energy, so we can define any arbitrary value and then define everything with reference to that. So we can just take that as 0, for example. So we can define, for example, in this particular case, our potential energy operator, this we have right here, as a function, as an operator that multiplies a function by 0. Okay, so when you do that, then what you're doing is you're just saying that the potential energy is constant, it's 0 at this time. So that's a potential energy operator. Here's an example. Let's say you have a 2-particle, one-dimensional harmonic oscillator. Okay? And that would be 2 particles constrained to move along the x-axis. You have an x-axis, and you get 2 particles. Okay? So that the interaction, the potential energy of interaction between them is given by this expression, 1/2 kr squared, where r is the distance between them. Okay? And the distance between them is what? Let's say particle 1 is located at x1, particle 2 is located at x2. What is the distance between them? Absolute value of x2 minus x1, right? Okay, so absolute value of x2 minus x1, that's your distance, that's your r, right? So what is r squared? So r squared is just x1 squared. So it's going to be 1/2 times the constant times x2 minus x1 squared multiplied by the function. Okay, so the potential energy operator is just an operator that multiplies whatever it's operating on by the expression for the potential energy. Okay? So this is the interaction between the 2 particles and no other sources of no external forces, no other sources for potential energy besides the interaction between the 2 particles. Let's look at this one right here. We have 2 electrons, electron 1 and electron 2. What's the potential energy of interaction between 2 charged particles? Remember from physics? Coulomb's law says the force between 2 particles is what? K Q1 Q2 over r squared, right? Or you can write it as 1 over 4 pi epsilon naught Q1 Q2 over r squared. What's the potential energy between them? Potential energy is just K Q1 Q2 over r. Okay? It's just 1 over 4 pi epsilon naught times Q1 Q2 over r. So instead of r squared, it's just r. Let's plot that just so you'll remember. Potential energy versus distance. Let's say you have 2 protons, 2 positive charges. What happens to this function at very small r? When r is very small, it becomes very large, potential energy approaches infinity. What happens when r approaches infinity? Approaches 0. So that's your potential energy function. Okay? Now let's interpret what this potential energy curve means. Okay, let's say you have, let's say this is the total energy of your particle, your two particles. Okay, so total energy is constant, right? Now, when they're very far apart, okay, there's minimal interaction between them. They're hardly aware of each other's existence, right? So the total energy is all kinetic. There's no potential energy. What happens as they approach each other? As they get closer and closer, going this way, remember, is shorter distance, right? What happens? What's happening to the kinetic energy? This difference between potential and total is just the kinetic, right? So this gap between that I'm drawing with my double-headed arrows, that's just the kinetic energy. So what's happening to the kinetic energy? Decreasing. What does it mean when the kinetic energy is decreasing? That means they're slowing down, right? Why is that logical? Two protons, for example, two positive charges approaching each other, slowing down. Yeah, they repel each other. They slow down. Okay, so that's what this potential energy curve means. The potential is rising, your kinetic energy is dropping. So as they're approaching each other, they're slowing down. Kinetic energy is dropping. Okay? And eventually what happens? Kinetic energy becomes so small until such time when the kinetic energy goes to zero. So at this point, all your energy is just potential. And so what happens when they reach that point? They're still going to repel each other, right? So where's the force now? It's going to be directed that way, right? So if the force is directed that way, they're going to separate. And if they separate, what's going to happen? They're repelling each other. So they're going to try to speed up, speed up, speed up. Kinetic energy increases. Eventually what happens? They become so far away from each other that the kinetic energy levels off. So that's how you would interpret that potential energy curve. Okay? Now, let's relate that to the expression for, let's do that for a proton and an electron. What would the plot look like? This way. Oops. What happens? So this time around, I have a proton and an electron. So Q1, Q2, this whole expression is going to be negative, right? So what does that give you? When R is very large, what happens? Approaches zero. When R is very small, becomes very large but negative, right? So the plot of your potential energy is going to look like this. It's going to approach zero as R approaches infinity, and it goes to a very large number as R approaches zero. Okay? So that's what your potential energy expression looks like. And that's what the curve looks like. And that's how you interpret. At very far distance, infinite distance, potential energy it's convenient to assume that as zero. Potential energy is zero there because that's where there's minimal interaction between the two particles. Okay? Now, you don't have to set it to zero. You can set it to some constant value. Like I said, there's really no absolute scale for energy. What we're really interested in is changes in potential. The change in the potential energy is just the reverse of the change in the kinetic energy. So when you say the potential is dropping, potential energy is dropping, that means kinetic energy is increasing. The potential energy is rising, that means while that's happening, the kinetic energy is decreasing. All right, so what would be our expression for the kinetic energy, potential energy operator here? It's just going to be 1 over 4 pi epsilon naught. And what's the charge of an electron? Negative E, right? What is E? Negative 1.602 times 10 to the negative 19 coulombs. Okay, so that's the value of E. And that's why an electron volt, okay, if you accelerate an electron through a potential of 1 volt, 1 electron volt, if you remember, was 1.602 times 10 to the negative 19 joules, right? 1 coulomb volt is 1 joule. So that's just a good way to remember the conversion from electron volts to joules. So that's 1.602 times 10 to the negative 19 coulomb volt. Okay, so it's charge of an electron times 1 volt is 1 joule. I mean 1 electron volt, sorry. 1 coulomb volt is 1 joule. So our expression here is going to be, so from now on, this means charge of the electron, right? So that's negative E. That's the other electron's charge. Also negative E divided by distance between the two electrons, so R. Okay? And then that is just a multiplicative operator. So if you operate that on a function, you just multiply the function by that. What's the expression for R? In terms of x, y, and z. If you want to do x, y, and z, normally you would use r theta and phi. It would probably be a better expression to use. But if you want to use r theta and phi, x, y, and z, what would r be? 2 points in space. What's the distance between them if you know x1, y1, z1? Let's just extend your Pythagorean theorem to 3 dimensions. So x1 minus x2 squared of x1 minus x2 squared plus y1 minus y2 squared. Your distance formula? Okay. Z1 minus z2 squared. Okay? All right. What is the complete expression for the operator corresponding to the potential energy due to Coulombic interaction? Coulombic interaction means electrostatic interactions, right? Okay, of electron 1 of helium atom with its nucleus. So you have a helium atom with a charge. What's the charge of the helium nucleus? How many protons in the nucleus? So the charge is plus 2e. For this nucleus, right? For the electron, so let's call this electron 1. What's the charge? Negative E. So what's our expression for potential energy operator? 1 over 4 pi epsilon naught. What's the charge of the electron? Negative E. What's the charge of the nucleus? Positive 2e over. You can just say, okay, let's just call that R1, the distance of electron 1 from the nucleus. And so that's, since we've written that as an operator, so we have to multiply whatever it's operating on by that expression. All right. The Hamiltonian operator is the total energy operator. So Hamiltonian operator, H hat, is just kinetic energy plus potential energy operator. And that's the definition of the Hamiltonian operator. So what would be the Hamiltonian operator for a hydrogen atom? Let's see. What do you have? What do you have in a hydrogen atom? You have a nucleus and you have an electron, right? So the total energy would be what? Energy total would be kinetic energy of the nucleus plus kinetic energy of the electron plus potential energy of the interaction between the nucleus and the electron. Okay, that's the total energy of any system of charged particles. Any system of particles, actually, in general, just kinetic energy of each one, add them all up, and then for each possible pairing of particles, you have a potential energy expression. Yes?
Should we not deal, is it always going to be dealt with the hydrogen atom?
No.
Or do you start inserting constants after?
Constants like what?
Or just...
Okay. So let's write the Hamiltonian for this. So you have a kinetic energy operator for the nucleus. kinetic energy operator for the electron and a potential energy operator for the interaction between the nucleus and the electron. So what was our expression for kinetic energy operator? Negative h bar squared over 2 times the mass of the nucleus del squared for the nucleus, right? What's the expression for the kinetic energy of the electron? Somebody call it out for me. Alex? Negative, so this is the nucleus. Negative h bar squared over mass of the electron over 2 times the mass of the electron. Del squared, not delta. Del squared for the electron plus. Jonathan, what's the expression for the potential energy operator? No, that negative h bar squared over 2 times the mass. That's for kinetic energy. 1 over 4 pi epsilon naught. What's the charge of your hydrogen nucleus? How many protons in a hydrogen nucleus? So the charge of the nucleus is plus E. Charge of the electron is negative E over R, the distance between them. Okay? So that's your total Hamiltonian operator. Now, if I wanted to write it in full, what would you have to do with this one? This would have to be written as what? A del squared operator is the sum of the second derivatives with respect to each coordinate. So this is partial derivative with respect to the x coordinate of the nucleus, right? Plus the second derivative with respect to the y coordinate of the nucleus, plus the second derivative with respect to the z coordinate of the nucleus. Okay, so may see what's this del squared for the electron?
It would be. It should be the same thing.
Yeah, so call it out for me.
What's that called?
Second derivative
Second derivative. What about the third derivative?
with respect to
X squared D.
okay, to the x coordinate of the electron, plus
Second derivative with respect to y squared E.
okay, second derivative with respect to the y coordinate of the electron,
Second
the second derivative with respect to
z squared E.
z sub e, the z coordinate of the electron. Okay, so that is your expression for the Hamiltonian for the hydrogen. And R is, of course, just the distance between the nucleus and the electron.
I had one that had multiple electrons, you just gotta keep putting extra T.
Extra T's and extra D's. That's, I think that's the next example.
Okay,
Hydrogen molecule. That was your
that
question?
was what I was trying to ask earlier.
Yeah. So H2 molecule. Let's look at H2 molecule. You have 2 nuclei, right? So to make a distinction, let's just call nucleus A, one nucleus A and the other one nucleus B. Okay, and so what's the charge of nucleus A? Plus E. What's the charge of nucleus B? It's also plus E. Each hydrogen atom has 1 proton in its nucleus. And this is H2, you have 2 electrons, so you got electron 1. And let's put electron 2 over here. Doesn't really matter where you put it. Okay? So what's our Hamiltonian operator? Kinetic energy of each one. So call it out for me, Ashley. First one, kinetic energy of of nucleus A, T hat A, plus kinetic energy of nucleus B, so TB hat, plus. We still have kinetic energies. We have two more particles. Kinetic energy of electron 1, so T hat 1, T1 hat. Kinetic energy of electron 2, T2 hat, oops, T2 hat, plus of interaction between A and B. Oh, what did I do? Okay. Right there. So VAB. So I'm just going to write that right now as V hat AB plus okay, so we're going to call interaction between electron 1 and electron 2. So I'm going to call that V hat 1, 2. Two more. All possible pairings of particles.
Potential energy of A and B.
A and electron 1.
Yeah. And then
Potential energy of interaction between A and electron 2. Oh, that's two more.
yeah, that's what I was wondering.
So 2. Another 2 would be what? B and electron 1 plus
I'll be an electron.
potential energy of interaction of B and electron 2. Huh? Yeah. You can see how it can get really hairy. But what we really do is we do a lot of simplifications, and you don't really do it this way for like a large collection, like a mole of particles, because that's impossible. So what you do is you would solve it for single H2 molecule, and then you apply statistical mechanics. So you do statistical averaging for to get properties like pressure and temperature. So that's a different subject. We can get to that after thermodynamics. Okay. So we're looking at just little particles first. Okay. So let's see. What would be the expression for T hat B? Negative over 2 times the mass of B, which is just the mass of the nucleus, right? Mass of B times del squared for B. What would this expression be, Chow? V hat 8. 1 over 4 pi epsilon naught times the charge of B, which is, what's the charge of B? A. What's the charge of A? This is A2, right? Positive E. That's 1 proton in the nucleus. Charge of electron 2, negative E, divided by the distance between nucleus A and particle 2. So this distance right here is RA2. Call that RA2, and that's what you write over here, RA2. Okay, so that's how you construct the Hamiltonian operator. You have a kinetic energy operator and a potential energy operator. Okay, so let's move on now to, what time is it? Okay, so let's move on now to postulate 4. Okay. Quantum mechanical operators representing system properties have a complete orthonormal eigenbasis. An eigenbasis is just a set of eigenfunctions. Okay, so in other words, if you have a quantum mechanical operator that you're using to represent system properties, then you have to postulate, we have to assume that it has a complete set of orthonormal eigenfunctions. So its eigenfunctions, if you list all its eigenfunctions, you can find a set that forms a complete set. What do we mean by a complete set? Remember we talked about a complete set last time? That means, what that means, okay? Any wave function, psi, that you can use to describe the system can be written as a linear combination of those eigenfunctions. So f1, f2, f3, and so on are eigenfunctions of your operator. Then you can write psi as c1 f1 plus c2 f2 plus c3 f3 and so on. Okay? And so that, and not only that, the probability of obtaining eigenfunction a sub I, okay, we're defining a sub I here is as the eigenvalue, eigenvalue. We're defining a sub I as the eigenvalue corresponding to f sub I. So if I have a hat, operator A, I'm interested in property A, okay? The property I'm interested in is A. The operator is a hat. If I were to operate on an eigenfunction of a hat, let's say f sub I, then I'm going to get back a sub I times the original eigenfunction f sub I, okay? So this little a sub I is the eigenvalue. What we're saying in this postulate is, remember we said if we measure A, the only possible outcomes are the eigenvalues, a sub I, right? A1, A2, A3, and so on. Now the probability that you're going to get a sub I is given by this, the square of this expansion coefficient. So c sub I squared, absolute value of c sub I squared, which we've already shown before is just going to be equal to integral of f sub I star psi theta, or this one. That's your c sub I. Okay, now let me just refresh your memory with that one. Okay, let's see. What happens if we take integral, for example, of f2 star psi theta? Just for example, what do you get? Integral of f2 star, and what's the expression for psi? c1 f1 plus c2 f2 plus c3 f3 plus and so on and so forth theta, right? So what do I do? Distributive property, I can distribute this, right? So this is going to be integral of f2 star c1 f1 theta plus integral of f2 star c2 f2 theta plus and so on and so forth, right? And what can I do with this at this point? Constant can be pulled out of my integral, right? So this is going to be c1 integral of f2 star f1 theta plus, I pull this one out, c2 integral of f2 star f2 theta plus and so on and so forth. What is integral of f2 star f1 theta? Your indices, you have two different orthonormal functions. 0. Why is it 0? Because we say f1 and f2 are orthogonal. Okay? So this is 0. And what is f2 star f2 theta? 1, because we say that your eigenfunctions that we've chosen a set of orthonormal eigenfunctions, right? So each function is orthonormal. So what are all the other values going to be? All these extra terms here. It's going to be 0. So here you just end up with what? C2 times C2. So you can see that C2 is just integral of f2 star psi theta. So in general, C sub I is going to be integral of f sub I star psi theta. Or you can write that in bracket notation like that. Makes it easier. Okay, so the probability that if you were to measure particular property A, okay, according to postulate number 2, the only values, postulate number 3, the only possible values you can get are A1, A2, A3, A4, those little a's, right? The eigenvalues. This postulate says What? The probability that you would get any one of those particular values would be equal. It would be equal to the square of, of the coefficient in the expansion of psi in terms of the eigenfunctions. Okay? So let's illustrate that with a simple example. Let's say a hat, okay, the eigenfunctions of a hat are f sub j, where a hat f sub j gives you back j times j plus 1 times alpha times f sub j. You notice, okay, alpha is a constant, okay, and j is 1, 0, 1, 2, 3, and so on. So what is f? What would be, for example, if I were to do a hat f0, what would my eigenfunction be? What is our j this time? J equals 0. So I get back the eigenfunction times f0. What goes here? What is j? 0 times 0 plus 1 times alpha. What is 0 times 0 plus 1 times alpha?
0.
That's 0. Okay. What about a hat f1 is equal to a constant times f1. What's the eigenvalue here? Remember, our eigenvalue is j plus 1 alpha, right? So what would this be? 1 times 2 times alpha. So in other words, we're saying a hat f1 is going to be 2 alpha, right? And a hat f0 is going to be 0 times 0. I'm sorry. This is 2 alpha times f1. And a hat f0 is 0 times f0. Okay, what's a hat f2 going to be? Something times f2. 2 times 2 plus 1, which is 3 times alpha. So it's 6 alpha. So you say a hat f2 is equal to 6 alpha f2. See the pattern? So what are the allowed values of property A? So based on this, what's the lowest allowed value of A? 0, right? So allowed A's would be A0, A1, A2, A3, and so on, right? What is A0? 0, right? What is A1? 1 times 2 alpha, so it's 2 alpha. What is A2? 2 times 3 alpha, that's 6 alpha. What is A3? 3 times 4 alpha, so 12 alpha, and so on. Okay, so if I were to ask you, what's the probability that if I made a measurement of A, I'm going to get 3 alpha? Is 3 alpha allowed? No. If it's not allowed, what's the probability I'll get it? 0. Okay? What's the probability that if I measure A, I'm going to get 7 alpha? 0. Okay? What's the probability that I'm going to get 2 alpha or 6 alpha or 12 alpha? Then I have to know what psi is. See? Psi gives you all the information that you need, all the accessible information. So if I want to know what's the likelihood I'm going to get 6 alpha if I were to make this measurement of A, then you say I have to know what psi is. Okay? And so let's say in this example, what if psi is given by this? 1 over square root of 6 f1 plus 2 plus 3 plus f3. Let's rewrite this. As C1 f1 plus C2 f2 plus C3 f3. What would that be? 1 over square root of 6 f1 plus 2 over square root of 6 f2 plus 1 over square root of 6 f3, right? Okay. What is a1? What did we say a1 was? 1 times 2 alpha, 1 times 2, so it's 2 alpha, right? So what's the probability that I'm going to measure A and I'm going to get A1? It's going to be, according to the postulate, it's going to be C1, absolute value of C1 squared, right? What is my C1? 1 over square root of 6. So C1 F1, C2 F2, C3 F3. So it's going to be 1 over square root of 6 squared, 1, 6. In other words, imagine you have billions of these identical systems. Okay? Identical, but if you measure, they have the same sign. But if you measure A here, you measure A here, you measure A there, okay? 1 out of 6, you're going to get 2 alpha, even though they all have the same sign. Right? So 1 out of 6 chance that if you measure it for this particular system, then that you get 2 alpha. Right? What's the probability that you're going to get A2? What's A2? 2 times 3, so that's 6 alpha, right? So what's the probability that if I measured A, I'm going to get A2? Then it's just going to be coefficient 2 squared. What's the coefficient of F2? 2 over square root of 6 squared, which is 4/6. Okay? What's the probability that I'm going to get A equals A3? What is A3? 3 times 4 is 12 alpha. So it's going to be what? C3 squared. Right? Probability that I'm going to get the eigenvalue, the third eigenvalue, it's just the square of the third coefficient. That's the third coefficient. 1 over square root of 6. You square that, you get 1/6. What's the probability I'll get anything else? All the other coefficients are 0, right? So even though, so what did we say this one? 2 alpha, you have a 1/6 probability. 6 alpha, you have a 4/6 probability, right? And 12 alpha, what's the probability? 1/6. 0 is allowed, according to this, but what's the probability I'm going to get 0? In this particular specific case, it is 0. Because C0 in this case is 0. Yeah. So if J equals 5, what's 5 times 6? That's 30, right? So what's the probability I'm going to get 30 alpha? 0. Even though it's allowed, in this particular case, because C5 is 0, the probability of finding 30 alpha would be 0. That's what it means. Okay? So that's postulate number 4. Okay. So this is the same thing we looked at earlier. So you have to imagine a very large number of identical systems, okay, where A hat, operator A hat gives you J plus 1 alpha times F sub J. So F sub J, we say, is the eigenbasis, the orthonormal eigenbasis of operator A. And then psi is equal to 1 over square root of 6, F1 plus 2, F2 plus F3. So if property of A is measured, what's the percent of the system that will give, what percent of the system will give you 6 alpha? 6 alpha is what? 2 times 3 alpha. So that means that's A2, right? So it's going to be, the answer would be C2 squared is the probability. So it's 2 over square root of 6 squared. That's 4 6. So 2/3. So what percentage? 66.7%. Okay, same system. What's the probability you're going to get 12 alpha? That's the eigenvalue of F3. We already, what was it? 1/6, which is 16 point something percent. Okay. All right. Orthogonality. We can actually prove that if you have non-degenerate eigenfunctions of a Hermitian operator, that those eigenfunctions are orthogonal. Okay? So, what does orthogonal mean? Integral of f sub I star fj d tau is equal to 0. If f sub I and f sub j are orthogonal, right? So here's the proof that you can actually, that if you have non-degenerate eigenfunctions, what does non-degenerate mean? They don't have the same eigenvalue, right? Different eigenvalues. So if you have a hat f1, gives you back eigenvalue little a1 times f1, and a hat operating on function 2 gives eigenfunction 2 gives you eigenvalue a sub 2 f2. So if they are non-degenerate, then a1 and a2 are not equal. Okay? So the way you would prove that, you should write something like this. You know A is Hermitian, right? So if you write something like f2 a hat f1 in brackets, so it's a, this would be what? Integral of f2 star times a hat operating on f1 d tau. But what's a Hermitian operator? If I were to switch f1 and f2, so now I have 1 on the left here and f2 on the right, I get the same thing provided I take the complex conjugate of that integral, right? So I'm just carrying this over here. That's the same expression. What did I do on the right side? I just applied the operator. Remember, that one I can take that in and out. Doesn't really matter, right? So that's a hat f2. And then what did I do here? The third step. Okay, a hat f1 gives you the eigenvalue a1, little a1 times f1. What did I do on this right side? A hat applied on f2 gives you eigenvalue a2 times f2. And I still have that star. Okay, and what did I do in the next step? I pulled out my constant from my integral. That's a1, f2, f1. What did I do on this one? Okay, now why is that star? Because of this star right here. So this is this expression right here. It's integral of f1 star a2 f2 d tau star. So if I want to pull out my a2, that a2 is going to have a star. Okay, pull it out of my integral. So this is really f1 star star. So this is really f1 and a2. This is going to be a2 star f2 star. Okay. So got to that point right there. What happens next? So here. Okay. What did I do next? I say that a2 star is the same as a2. Why? It's a real number. Why is it a real number? We've already proven earlier that eigenvalues of Hermitian operators are real. And we're saying that a2 is an eigenvalue of a Hermitian operator, so it has to be real. So a1, same thing on the left. So a2 star is now a3. What is f1, f2 star? What did I do from here to here? I switched 2 and 1. So if I write f1, f2 star, if I switch those two, f1, f2, f1, and then I do star star on the outside, right? So I remove the star. So we made it through here. What does this imply? F2, this is like the same thing, right? So it's like saying A1 times X equals A2 times X. Well, if A1 and A2 are not the same, they're not equal. If A1 and A2 are not equal, what should X be? If I say 3X equals 4X, what's the only possible X that would satisfy that? 0. So X has to be 0, right? So you say F2, F1, that in brackets must be equal to 0. So what we did is we just proved that if you have non-degenerate eigenfunctions of a Hermitian operator, then they are automatically, if they don't have the same eigenvalue, automatically you know that they are orthogonal. Okay? That's why we say we can pick an orthonormal set of eigenfunctions for a Hermitian operator. Okay? So, but if they are degenerate, okay, they need not be orthogonal. But you can make them orthogonal using what's called as the Schmidt orthogonalization procedure. Okay? And I think I have it right here. So, in other words, it's possible for us to choose a set where everything is orthogonal to each other. Okay? Now, remember we said that we postulate that the Hermitian operator representing a property of the system has a complete eigenbasis. Okay? The eigenbasis, which is a set of eigenfunctions, we only need to include linearly independent functions to form a complete set. What do we mean by linearly independent? If I have function f, okay, and g, if I can write function f as constant times g, is it time to go? Okay. Now let's pick this up next time. We'll continue this next time.